Hi, and welcome to an example using the law of exponential change. Before we actually do our example, I want to go through the variables in this equation and make sure we're familiar with what each stands for. Y naught is your initial amount or your starting amount. K is your growth or decay constant depending on what you have. If K is greater than 0, it's going to be the growth constant, and if K is less than 0, it's going to be the decay constant. So let's just call it the growth decay constant. And then finally, T is the amount of time you have, and time could be measured in hours, in half hours, in half-lives. It just depends. So T is your time, amount of time. All right, and then finally, your Y is your ending amount, the amount you end up with after your given starting amount has gone through a certain amount of time. So this is the amount you end up with, or your ending amount. All right, make sure you're clear on what these variables mean. We're going to go ahead and work through an example using these variables. All right, in this example, what we're supposed to do is find the half-life of a radioactive substance with the decay equation y equals y naught e to the negative kt. Now you want to be careful here. They've kind of built in that negative, they've built the decay factor into this equation, so you have to take that into account when you're doing the problem. So they don't tell us how much we start with and how much we end with, but we do know that we've got a half-life here. And if you recall what half-life means, it's the amount of time it takes for a substance to be reduced by 1/2. So it's the amount of time it takes for a substance to be reduced to 1/2 of the starting amount. So if you know this definition, you can kind of invent your own numbers. So if we start with, let's let y naught equal 10. If we start with 10 units of the substance, then we're going to end up with 5 units after 1/2 life. Okay? So if we plug these numbers into our equation, basically what we're being asked to do here is plug in these numbers and show that the half-life, which is our t, depends only on k. So we want to leave the t and the k into our equation and solve for t. If we solve for t, we'll show that the half-life, the time, depends only on k. So let's go ahead and do that and see what happens. If I put in 5 for my y, we're going to have 5 equals y naught is our 10 times e to the kt. All right, now our job is to solve for t. In order to do that, you first want to get this by itself. So let's divide both sides by 10. And if you do that, you get 1/2 here. And there's your half-life. That's essentially where it comes from. And then if we continue to solve, we get 1/2 equals e to the kt. Now to get rid of an exponential, you need the inverse of that exponential, which is a logarithm. So if we take the natural log of both sides, we get natural log of 1/2 equals the natural log of e to the kt. And if you remember, this can come out down in front, and the natural log of e is 1. So we get kt equals the natural log of 1 minus the natural log of 2, and we can split that division problem up using the law of exponents. And then when we simplify that, natural log of 1 is 0. The opposite of the natural log of 2 is what we're left with, and we have the kt here. Now remember, in our original equation we had negative kt, so we're going to take this negative sign and put it over here. Okay, and that will essentially get us the negative k that we had up here. So if we solve for t now, we get the natural log of 2 divided by the opposite of k equals t. Or you could say that t equals the natural log of 2 over negative k. All right, what this shows is that the time, or the half-life, is solely dependent on this decay constant. And because the k is negative here, that's going to be a decay constant. because we have the negative sign built in. We don't have to say k is less than 0. We're treating k as something positive, and this negative sign indicates the decay piece. So our decay constant is here, and this indicates our half-life. This has some interesting effects, and this is something you do want to memorize. So going back to what we have initially, so our generic equation is y equals y naught e to the kt. If you're using this generic equation, you can remember that your half-life is always going to equal to the natural log of 2 divided by the opposite of k. Or you could also say that k is equal to the natural log of 2 divided by negative t. So you kind of have these two pieces that help you solve a lot of problems without going through the entire process that we did up here. So these would definitely be things you want to highlight and memorize to use in future problems. All right, so next time you do a half-life problem or a doubling problem or a tripling problem, this relationship can apply and save you some time. I hope this helped. Keep working through more examples.